SwayamPrabha. Digital India. Educated India.
Right, ठीक है जी। Good morning. Today we will discuss about rotordynamics. As you know, in any machinery, rotating shaft is a very critical component. So, in this lecture on rotordynamics, I will be just covering the basics of rotordynamics from a condition monitoring point of view. In fact, rotordynamics itself is a full-fledged 40 hours course, and in this lecture of 1 hour, we are just trying to discuss about the important aspects of rotordynamics and how actually the problems of unbalance in a rotor, misalignment, and the effect of the support stiffnesses play a role in the dynamics of the rotating shaft system. Okay. And in practice, we will be finding many rotor systems comprising of turbines, compressors, pumps with impellers, sets of impellers, or fans with sets of blowers, and so on. So, rotordynamics is very important that we understand the physics of such rotating machines, and then how do we try to control the unbalanced forces, control the rotordynamic stability, etc., calculate the critical speeds, and so on. So, the basic objectives of rotordynamics is predict critical speeds and so on. But let me explain to you what I mean by a rotor system. I have a long rotor which is essentially supported in some sort of a bearing. And this is undergoing a speed of rotation omega, it is rotating at a certain speed, and this is the span of the rotor. Okay. These bearings have certain stiffness, say K1, K2, okay, and there could be a heavy mass M on the rotor. So, if this rotor stiffnesses are constant and stiff, from the bearing supports are rigid or soft. When we have rigid stiffness on the supports and the simple disc which is rotating, this is basically a disc. We have the simple Jeff-Cott rotor. Many physics is understood by understanding the Jeff-Cott rotor, where we have a rigid support stiffness and then we have a certain disc which is rotating. So, when they are rotating, we will have what is known as the critical speed, a certain speed at which the speed is equal to the natural frequency of the system, and then we are going to have the condition of resonance. So, this is very important in the rotor systems. Well, I have shown here one disc, there could be multiple discs. For example, in actual conditions, think of an aero engine. or aircraft engine, which is essentially a gas turbine engine. So, we have a long system wherein we have the first stage is maybe a compressor set, and then we have the high pressure turbine, followed by another low pressure turbine. We have the air coming in, inlet air, maybe some sort of a fan could be here. Fan, and these compressors, there are a lot of set of vanes, and same is true in the case of turbines. And then we have the exhaust, which essentially gives the thrust to the engine for propulsion. Of course, in between we have the combustion system. Of course, no, I am not going to go into details of the gas turbine, but essentially our domain of interest is this drawn here in red, and then this portion here, and this is the long shaft, which are essentially, these are all supported on maybe bearings, intermediate bearings. So, a typical gas turbine engine has this kind of a configuration, wherein on a long shaft I have a compressor followed by a set of couple of high pressure turbines, low pressure turbines, and each of these system rotates at a very high rotational speed, and typically of the order of 30,000, 40,000 RPM. So, you can imagine we have such a engineering complex system, wherein on a shaft I have sets of vanes or blades which are mounted on discs. There could be multiple discs, and they are rotating at a very high RPM. Now, think of a scenario, there could be many issues. One is, what if the rotating speed, it has a speed which equals to the natural frequency of the system. Okay. Then there will be condition of resonance. So, condition of resonance occurs when this critical speed is equal to the natural frequency of the system. So, when a aircraft is rotating, or the engine is rotating and it is powering the aircraft, and there could be conditions of resonance, and because of this what could happen is there could be large amplitudes and large motions, and this shaft, because of resonance, if it is going to have large motions, okay, it may so happen, if this was the casing, okay, and then this blade sets may touch the casing. So, there could be literal rubs. Okay. So, this can lead to lot of things, high amplitudes. This could further lead to rubs between rotor system and the stator. In this case, it is the casing. So, a lot of wear and tear will occur, materials may fail, components may okay. And then this is one instances. So, by studying rotordynamics, if we can physically model such a system, okay, through techniques of the analytical formulation or through the techniques of or finite element method, okay, we can try to estimate the critical speeds and avoid them during the operations. So, this is what is one of the one of the important objectives of studying rotordynamics. The next is determine design modifications to change critical speeds. We can change the do certain design modifications to change the critical speeds. Through these mathematical models, we can change the mass, stiffness of the appropriate system and change the critical speeds, omega n is equal to root over k by m. So, we can play around as a designer, we can play around with the values of k's and m's and change the critical speeds. We have in one case wherein there is lot of rotating systems, many rotating systems, subsystems in one unit. That could be, for example, a motor driving a gearbox, driving a set of blades. Okay. So, and they are all rotating, the shafts are rotating. Okay. Motor driving a gearbox, driving a set of blower. Okay. All of them have rotary inertias, and then they have the corresponding the rotary displacements, etc. So, such subsystems, okay, can have the and then you have the natural frequencies. Like in the case of a linear system, we had multiple degrees of freedoms and every degree of freedom has a corresponding natural frequency. When you have the torsional rotating systems, every subsystem, subsystem 1, subsystem 2, subsystem 3, each of the subsystems can also be having natural frequencies, and these are basically torsional natural frequencies. And if we can predict them and then know them beforehand, we can as a designer or an operator ensure that we do not run the system at its natural frequencies. Okay. So, estimating the critical speeds, doing design modifications and then estimating the natural frequencies of torsional vibration is very, very important in the study of rotordynamics. Okay. And the next would be in a rotating system, if you think the case of an like the gas turbine we just talked about, there is a small amount of unbalance in one of the vanes or the blades, and once they rotate at high speeds, we will be having very, very high unbalance forces. Okay. And these forces are radial in nature and because of this unbalanced forces, we will be having forces at the bearing supports, and sometimes these forces could be very high, and then we have to ensure how to reduce these forces, otherwise the bearings do not come off the supports, or the bearings are not able to withstand such high forces. So, as a good designer, we have to ensure that the unbalanced mass rotates at its center of rotation, or everything is centered around the rotation and not away. Suppose I have an unbalanced mass m at a distance r, I am always going to have an unbalanced force m omega square r, and this is going to be harmful to my bearings. If I put the bearings here, they will be harmful. So, this has to be calculate the we can do the balance correction and locate a location from the measured vibration data. Now, when you talk about balancing in the few classes down the road, we will see how we can balance such unbalanced forces either in single plane or in multiple planes, and give correcting unbalanced masses, so that the net effect is reduced. For example, in this case, if I have an unbalanced mass at a distance r on this direction, I can give another unbalanced mass of the same quantity at a distance r opposite. If I draw this plane, if I have an unbalanced mass, if I have unbalanced mass here, okay, I can give a correction mass here. Okay, I can reduce this forces, okay, the net forces. And then another problem is, we can also predict the amplitudes of this vibration caused by such rotor imbalance. Now, I am having these two words synchronous. So, if when a system is rotating at a particular RPM, we denote it, so omega, as 1 times x, which is the rotational speed, and any vibrations at this frequency is actually known as the synchronous vibration. So, any frequency less than omega is sub synchronous, and any frequency greater than omega is super synchronous. Okay. Later on, you will see when this rotating shaft is rotating at a particular speed, having a disc. Okay. There will be speeds at which there will be a lot of dynamic instability. Okay. And in fact, this is one of the serious problems in the limitations of rotor speeds. In particular, if you plot it as omega, maybe the amplitude of at certain speeds, it will happen. Okay, these are the which in this case, if we increase the speed, so there is a critical speed beyond which we should not operate, or if we have to operate it, how this can be controlled. And the I will just tell you right now, by controlling the damping at the supports, we can control this dynamic instability in rotor systems. And there are many ways to suppress this dynamic instability. This is essentially by designing or incorporating or changing damping at supports. And this has been possible by, if you think of by having what is known as a squeeze film damper in the case of journal bearings, and sometimes in rolling element bearings, which are essentially very high stiffness bearings, okay, almost rigid supports. In some way, by having an SFD, squeeze film dampers in the outer race, some amount of damping control can be done. Of course, people have used magnetic bearings to control dynamic instability in rotors, okay. And that is still right now in still in a research stage, I would say, or very few practical applications have come out of magnetic bearings to control the dynamic instability. In small systems, they have been successful, but in large systems, there are other issues with using magnetic bearings. But traditionally, squeeze film dampers have been used in the case of journal bearings to suppress this dynamic instability. And though we use rolling element bearings, some amount of SFD, particularly in aircraft engines, this has been done to support the dynamic, suppress the dynamic instability. So, to summarize, the objectives of rotordynamic analysis, as I have listed here, are predict the critical speeds, determine the design modifications to change the critical speeds, predict natural frequencies of torsional vibration, calculate the balance correction masses and location from measured vibration data, predict amplitudes of synchronous vibration caused by rotor imbalance, predict threshold speeds and vibration frequencies for dynamic instability, determine design modifications to suppress dynamic instabilities. Now, there is a lot of things happen when we are rotating a shaft at a particular omega. Okay. So, there will be a whirling of the shaft, okay, and this is the bow of the shaft. First assumption is we have considered the shaft is flexible, so that it can bow. Okay. So, this whirl amplitude, maybe if I denote it as u, is the our objective is to reduce this whirling amplitude, because what happens if it whirls, sometimes it may foul with the casing in a system. Suppose this is my casing. So, once it touches here, these are the regions where rubs are going to occur, and this is going to create wear and tear. excessive force and then material may fail. Okay, as I was telling you, to reduce the synchronous wheel amplitudes, I have to balance the rotor, so that this unbalanced mass is a minimum. So, it does not fly out, or avoid rotating at that particular speed omega. Try to change the speed, and if nothing is possible at this bearings, we can use SFD, so that the support forces onto the bearings is going to reduce. Okay. Now, if I think of a rotor system, suppose let me just draw this. The ratio of the dynamic force to the forces on the supports when the supports have a rigid stiffness. And this is u. And now, if I increase the damping, where F infinite is the force at the support in the case of rigid supports. Example, our rolling element bearings. So, if I have a shaft which is supported on rolling elements bearing, okay, and if this is going to have an amplitude u, the F infinite any location will be half m omega square u. Okay. And you will see for large machines this force is very high. When the m is high or at high speeds, the forces are very high in case of large rotating systems. When you are talking about, say, a steam turbine, which is essentially used in say power plants. Okay. The force, if they were supported on rigid bearings, okay, like rolling element bearings, ball bearings, etc., the forces on the support would be very high. Okay. And we have to, and there is no way, no mechanism, no physics by which we can reduce this forces which are coming to the supports. There are another way by which we can reduce these forces, okay, and that is where, which is known as the journal bearings. Okay. But I should just give you an example. In journal bearings, essentially what happens, I will come to the journal bearing first. Suppose I have a shaft which is rotating, okay, and this is filled with oil, and because of the eccentricity between the center of the journal and the center of the shaft, okay, I will have a converging diverging section, okay, and this shaft is rotating like this and the journal is fixed. Okay. Because of this converging diverging section, there will be a fluid pressure. Okay. This hydrodynamic force, which happens because of the converging section and the fluid's viscosity, the load of the shaft, load which is coming mg, can be supported by the bearing forces, because this will give a lift force. So, when I rotate a shaft at an omega, okay, in a journal wherein it is filled with a viscous fluid, because of the eccentricity E, okay, this fluid will try to build up a pressure, okay, and this pressure is going to act in the upward direction and support the weight which is coming at the support. So, in the journal bearings, essentially the fluid viscosity comes into play, and we can introduce damping, okay, and thus reduce the force which is coming on to the bearing. If I go back to this plot here, this is because of the journal bearing, and this is because of the rolling element bearing. So, I can reduce the loads coming to the supports by introducing damping, which is only possible when a journal bearing. So, in any system, like in the case of the steam turbines, power plants, if I have a large system or large shaft or long shaft carrying a lot of disk of the compressors, turbines, etc., and if they were supported on rolling element bearings, what would happen is a lot of forces would come onto the supports. Okay. Instead, if I use a journal bearing, and then in journal bearing is because of the fluid viscosity and the eccentricity of the shaft from the center of rotation, I will generate a fluid pressure acting in the upward direction, and then this is able to support the loads coming onto the supports and reduce the forces. And this can be very easily controlled by varying the amount of fluid flow, the viscosity, etc. This can be changed, and then I can reduce the forces. So, invariably in many of the stationary plants, you will see that the large plants which are on earth, on ground rather is the better word to use, we can have journal bearings, okay, which will try to reduce the forces coming onto them. And on this journal bearings, if I have a squeeze film dampers, basically I have a system wherein I am squeezing and having a vertical motion radially. Okay, I can put a squeeze film dampers, and basically, and this is made to oscillate along the outer race, and then this basically this I can introduce damping. And as you have seen, by introducing damping, at the supports, the load which is carried at the supports does reduce, and this is so damping has a very important role in rotordynamics, as to it can reduce the support forces, it can control instability. Okay. So, if I have to go back, the effect of the support bearing stiffness, bearing support flexibility can greatly reduce the dynamic load transmitted through the bearings, like we just discussed. By having the support flexibility properly selected, I can reduce the dynamic load which is transmitted through the bearings. Bearing support damping increases the dynamic load transmitted through the bearings at high speeds, as is also obvious from that plot. Bearing support stiffness may be necessary to keep the transmitted load within acceptable limits while traversing the critical speed. Okay. Improperly chosen support parameters can produce dynamic loads in excess of the rigid support values. And imagine in the I have chosen certain parameters of damping such that the forces are very high, then we are going to have a failure of the supports, okay, and this will not be accepted or allowed. So, how we can reduce that? Now, what do I mean by rotordynamic instability? Supersynchronous vibrations due to shaft misalignment. Okay. Subsynchronous and supersynchronous vibrations due to cyclic variations of parameters mainly caused by loose bearings or shaft rubs. Non-synchronous rotor wheeling that becomes unstable. Okay. So, these are the conditions wherein we have to be careful to avoid such conditions. So, we need to obviously have a shaft which is perfectly aligned. We should not have any loose components which will give rise to shaft rubs. Okay. So, these are the conditions which we can avoid, so that the rotordynamic instability does not happen. Okay. And with this I will tell you there is one, suppose I have this RPM curve, and these are the first natural frequency, second natural frequency. So, there will be some frequencies, and these are basically known as the Campbell diagram. So, there are regions on which you would like to avoid operating at these zones, okay, wherein your runoff speed should be such that you are operating at a speed at which you are below this natural frequencies, or operating at a speed you are in between these natural frequencies. So, this kind of RPM which is natural frequencies plots are to be generated for multiple rotor systems or large rotor systems. So that the conditions of resonances because of the critical speeds are avoided. Okay. So, with this basic understanding about the importance of support bearing stiffness and how support bearing stiffnesses contribute to the overall forces which are coming onto the supports, when we design a turbo machinery, these are some of the things which one needs to keep in mind. Avoid critical speeds if possible. If you have to operate through the critical speeds, traverse it very quickly. Like in suppose a gas turbine, we have to rotate at 30,000 RPM. Once you go from start to 30,000 RPM, I am sure there will be number of resonances you have to pass through. So, quickly you need to change over to the resonance, quickly you need to move into the operating speed of 30,000. We cannot be moving or rotating constantly at the same natural frequency. So, the ramp up or the speed up has to be very, very high. Minimizing dynamic response at resonance, if critical speeds must be traversed, is just what we discussed. We need to move up the speed increasing mechanism very quickly. Minimize vibration and dynamic loads transmitted to the machine structure throughout the operating speed range. Avoid turbine or compressor blade tip or seal rubs. Avoid rotordynamic instability. Avoid torsional vibration, resonance or torsional instability of the drivetrain system. So, as you can imagine, a turbo machinery is a very, very complex mechanism. Other than the fluid mechanics operations, the fluid machines part of it, wherein we have a certain energy coming in, certain energy going out, and then we get a thrust. But beyond that, there is a lot of engineering into designing a perfect turbo machinery as to its dynamics is concerned, in terms of not rotating at its critical speed, how to avoid critical speeds, how to traverse up high speeds, how to avoid instability, how to avoid rotor rubs between the stator and the rotors. So, these are, and how to avoid multiple resonances in torsional systems. So, these are the complex issues of turbo machinery. We can talk of our aircraft engine, steam turbine, even a large set of pumps, but these have to be taken into account. This, some of them are vertical. If you go to many of the power plants, particularly the hydel power plants, you will see a lot of the vertical, maybe the Kaplan turbine, etc. Vertical turbines, the shafts are not horizontal, but vertical. We have the effect of the gravity loads altogether on the bearings. How do you select the bearings, the thrust bearings, the pivot bearings, the pad bearings, etc. Now, how do you take care of these issues? So, a turbo machinery from a dynamics point is a very, very complex thing. As a designer, people do take care of it, but then our goal in this class is how do we maintain and monitor the health of such a large complex turbo machineries. So, just to recap, we have already discussed about the bearings. So, bearings essentially are of the two types, the rolling element bearing or the journal bearing, fluid film bearing. And as you know, in the rolling element bearing, we have the outer race, the inner race, and the rolling elements. Which could be either a roller or a ball, and then they are supported by what is known as a retainer or a cage, which ensures that the no two rolling elements come in contact with each other. And basically, they are used for rigid supports. So, in essence, rolling elements are good where the forces on the supports are less, because when the forces are very, very high, because of the physical dimensions of the bearings, they may not be able to support very, very high loads, as in the case of the turbines, which we discussed about. But the other kind of bearing is the journal bearing, or the fluid film bearing. So, basically in the journal I have a shaft, and because of this film and because of this converging diverging section and because of the eccentricity of the shaft, there is a pressure buildup, and this pressure is actually supporting the shaft. Okay. So, in no point during rotation there is any rigid contact, no rigid contact between the shaft and the journal, only maybe at rest. Okay. This is in contact. So, every time you start or stop a machine, the entire rotor system comes and sits on this. So, there is a lot of wear and tear in the journal, wear and tear in the journal. That is why these journals are made out of soft materials, soft bearing material like babbets, etc., which can be withstand a high temperature as well. And which should be able to. So, because of the physics of the journal bearing, they can support large loads. So, basically all the steam turbines, etc., or the gas turbines which are land based, we have journal bearings. Okay. And basically this film lubrication is the hydrodynamic lubrication which is occurring. But in this journal bearings, the pressure was actually built up because of the eccentricity of the shaft and the journal, and thus creating a converging diverging section. But if I have a source of externally pressurizing the fluid and applying it to the journal, I could be supporting the large loads which are coming at the bearing supports, and such are the hydrostatic bearings. And of course, we are not going to go into the details of the bearings, but as opposed to hydrodynamic bearings or the journal bearings, there is never any contact between the shaft and the journal. So, very precision instruments or equipment have such hydrostatic bearings, wherein we apply externalized pressurized oil or lubrication into the journal and the shaft. Okay. And then, but in our case we have the journal bearings or the rolling element bearings. So, in rolling element bearings, if I in the outer race, if I have some provision of adding a squeeze film damping arrangement, wherein I can change the damping arrangements, which is there actually in the aircraft engines. Other than the rigid rotating element bearings, they also have a squeeze film dampers on the periphery, which will not rotate, but only oscillate, and thus create this damping. And as you know, because of the damping, the forces on the bearing support comes down. But when we talk about a journal bearing, we can have the cases wherein because of the fluid wedge conditions, the oil is lifted off, or the oil picks up and gives a pressure, and the support shaft is picked up, is held at a position. But then in rotordynamics also we do a lot of tests on the rotordynamic systems to understand from a condition monitoring point of view or from a dynamic analysis point of view. These are some of the tests which are done on the rotordynamic systems. One is to begin with is the static stiffness test, or what is known as the impedance measurements of the system. So, at the bearing support stiffness, okay, at one location, I can give a force and measure the deflection. Okay. Okay, by having a transducer, this deflection could be measured by an LVDT, or even you can put an accelerometer and then integrate it to get the deflection. So, just to know the static stiffness K delta, I can use such an arrangement wherein we give in a force, measure the deflection and find out the static stiffness. Okay. Many times to understand the cases of the resonances, we can do a co-stop test, wherein we increase the RPM, okay, at a particular rate, or come down from high speed, coast down. Particularly in the case of the journal bearing, a very important thing happens. Like in this journal bearing, you would think here basically the forces here at the, if you enlarge this, okay, one is at rest and other is moving at a speed of omega, okay, v by r, so linear speed. So, there will be a point wherein the entire film in the middle will be having a speed of omega by 2. Okay. So, this fluid in the wedge is approximately theoretically moving at a frequency of 0.5 omega, or the fluid is churning. Fluid is churning is the, or whirling at a speed of 0.5 omega. Okay. But usually because of the frictional losses, this frequency is around 0.42 to 0.48 of f, where f is the rotational speed. Okay. So, anytime I am having a shaft rotating at a frequency of f, I will see a predominant frequency somewhere around 0.42 to 0.48 f. So, when you do a coast up and coast down analysis, you will be very easily seeing the effect of whirling, and this can be removed by changing the damping, etc. Okay. In the laboratory, we have rotor rigs, wherein at one end we have a journal bearing, wherein we have a particular type of lubricant, and then say for example, an oil, and next time we have a kerosene, you will see the effect of whirling pretty much there. Okay. Many times we do a lot of constant speed measurements in rotor systems, okay. And of course, the last one is the resonance test, which we do on the rotor systems to find out the natural frequencies of such systems, so that we can avoid rotating at the natural frequencies. So, some of the common faults which occurs in turbo machinery are the cases of imbalance, misalignment, load variations, mechanical loosenesses, critical speed or resonance, excessive clearance in the fluid film bearings, rotor rub, oil whip and oil whirling. Another important thing happens as an oil whip. For example, we are going at a rotating at a particular frequency, but this frequency happens to be an oil whirling has occurred. Oil whirling occurs at 0.42 to 0.48 f is this oil whirling occurs. What happens? There will be some multiples at which this will be equal to the natural frequency of the system. In such a case, the okay, and then this is going to whip around at that frequency. It is going to bow, and then it will be latching on to this frequency, and that is known as whipping frequency. This we will discuss when we talk about the case of unbalanced responses and rotor systems, where this whipping occurs. Okay, so to summarize, in this class we discussed about the requirements on what we do in rotordynamic analysis, how basically the bearing support stiffness and in particular the damping plays a role in the support forces which come to these supports, and then how we can select the kind of bearing, the rolling element bearings or the hydrodynamic bearings to take care of the loads, and then what are the defects which could be there in rotordynamic systems, and then how we avoid them. Okay. Thank you.